Hello everyone and welcome to my presentation. I am Adnan Zaman. Today I will be presenting our work titled Peak Prediction using Multilayer Perceptron for Edge Computing ASICs Targeting Scientific Applications. This is the outline of my presentation. First, I will try to motivate the reason behind choosing Edge AI ASICs for our use case. Then I will explain how did we move towards Edge AI ASICs. Then I'll talk about the main contributions of the work, then talk about the neural network model and how did we train them, and then I will explain the overall workflow that we come up with, and then I'll talk about the architectural exploration that we did to optimize the design. Then I'll discuss about the experimental results and I'll conclude after that. Now the question may arise, why did we choose AGI ASICs for our use case? The reason is there are some applications that perform better utilizing ML algorithms and need to be run in real time. Edge AI provides us these benefits along with the most important one. It reduces the data bandwidth by processing data on the detector and only sends the important data to the storage destination for further analysis. The important criteria that we need to remember, these devices should be of compact size and also it should consume very limited power. The challenge is more prominent as the high data rate detectors play an integral part in scientific research and it generates huge amount of data. Then we brought the question forward, uh, would Edge AI ASICs reduce the data bandwidth and storage requirement? To understand the basis of integrating ML ASICs on the front-end electronics, we can see the conventional readout system. A typical particle detector signal processing chain comprises of analog processing components such as amplifiers and shapers, and it ends with digitizers. The digitized data then sent to offline for further processing. For our use case, it goes to digital signal processor that perform fitting or interpolation to predict the peak amplitudes in the detector's sensor response. Though this fitting procedure is expensive and it is very difficult to implement on the chip. Hence, we think it is imperative that we explore the feasibility of implementing ML algorithm on the front-end ASICs. The task of the neural network circuit is to determine the energy deposited from the time-ordered samples, that is, the peak amplitude of the sample waveform snippets that we see over here. The network should predict these values instead of finite and variable profile of the signals from the sensor and the imperfection of the filter. In doing so, we try to achieve the goal of implementing this hardware with better power performance and area numbers. The main contributions of the work can be summarized as follows. We tried to demonstrate a feasible ASICs design flow to predict the peak amplitude of the sensor signal. We do design space exploration from both software and hardware perspectives. We also try to achieve least latency through different architectural optimizations. The ground truth parameters, that is the energy deposited in a detector, are being processed in an analog processing chain to generate a set of sample waveform snippet. When we pass it through the neural network, it tries to predict the peak amplitudes from these waveform snippets. We have multi-layer perceptron with 4 hidden layers to do this work. And we also try to avoid computationally expensive operations such as exponentiation and deviation by restricting activation functions to ReLU. We generate almost 10K sample waveform snippets, 90% of them for our train and validation and 10% for testing. We also utilize network quantization technique where parameters are represented with 8 or 16-bit fixed point instead of 32-bit floating point. We also use quantization-aware training where weights and biases are represented with low precision bits. Here we demonstrate the overall workflow that we followed to produce the get level net list starting from ML algorithm. We have a 5-layer MLP with relay activation trained in QQRS that goes through an open source tool called HLS for ML that converts the trained model to equivalent C++ source codes. But these source codes are tailored for FPGA route. So we take this source code and do some processing to make it ready for the Mentor Catapult, that is a high-level synthesis tool. We generate RTL code from the C++ source codes. While generating the RTL code, we do some design space exploration to come up with the design with least latency. Then this generated RTL code goes through a logic synthesis tool in a commercial 65 nanometer process node to get the get level netlist. Here we see how a sample MLP network can be represented with block level modules with input-output interfaces. The weights and biases are read through a test bench and provided to the correct modules. The output from one module goes as an input to the next one. It operates just like a data flow graph. We do design space exploration both from software and hardware perspective. From software perspective, we do bit precision exploration. As we see from this table here, floating point computation is costly. That's why we resort to quantization-aware training, where parameters are represented with 8 or 16-bit fixed point instead of 32-bit floating point. We further the QET by varying the precision bits of weights and biases by 4, 6, and 8 bits. As we can see from the graph here, we calculate MEEs for different model sizes and for different bit precision configurations. And as we move towards the hardware realization, we'll also see the effect of varying the bit precision in the power, performance, and area number. Also, quantization and overflow logic may add extra hardware and latency to the design. We also consider this factor here. From hardware perspective, we do architectural optimization to achieve a least latency design while doing the high-level synthesis. We observe that memory access is the bottleneck to achieve a maximum parallelization. We need to leverage data reuse and parallelism. High-level synthesis lets us choose between registers or memories. We can change the word width, or we can split the memory into multiple memory banks. This allows us to match the ML algorithm bandwidth to the memory bandwidth. One of the primary approaches to optimize the design is by constraining loops. It's a three-pronged technique that allows us to unroll, merge, and pipeline loops. Loop unrolling dictates the number of times the loop body is copied. It adds parallelism to the design by making multiple copies of the loop body. We can achieve a minimum latency by prudently choosing either to completely or partially unroll the loops. Excessive unrolling, though, gives us least latency, but it comes with the penalty of extra area. As you can see from the example here, if we have a for loop with 4 iterations, if we keep the loops rolled, then we'll have one multiplier on a register and one a single adder. But if we choose to fully unroll the loops, on representation of the hardware can be this. Here we have 4 multipliers and 4 registers, and we have multiple adders in the design. Though it gives us least latency, but we'll have the penalty of extra adders, multipliers, and registers here. After the loop unrolling, we can do the loop pipelining. It is the process of dictating when to start the next iteration of the loop. It improves the latency and throughput of the design. We have to remember that fully unrolled loop cannot be pipelined. The next step that you can take is loop merging. It allows us the parallel execution of loops that usually executes in series. Through these techniques, we can achieve a design that is optimized for least latency. To validate our proposed approach, we conduct different experimentations at different steps of the workflow. As seen from the table here, we consider 4 different configurations of MLPs depending on the number of neurons on each hidden layer. We arrange the weights and biases of 4 hidden layers in 2 different groups, each having the option of being represented with either 4, 6, or 8 bits. As an example, let's say 6 denotes weights and biases of first 2 hidden layers that are represented with 4 precision bits, and next 2 layers with 6 precision bits. With this consideration, we obtain 9-bit precision sub-configurations for each MLP configuration. For each MLP configuration, we calculate mean absolute error from QKeras, HLS for ML tool, and then from the RTL generated through the HLS, and then we compare. Here we see the ME numbers. We observe that ME variation between the QKeras and HLS for ML is in the range of 0.2 to 1.2%, and we get a complete match between HLS for ML and RTL. This verifies that our proposed methodology, starting from QKeras to RTL generation, stands correct. It confirms the seamless transition. To explore the relation of network model size with accuracy, we compute mean absolute percentage error of RTL netlist. As seen from the figure here, the general consensus is as the network grows bigger, the accuracy improves. We do observe a couple of outliers. As an example, if you look at the configuration here, the accuracy of this network is less than the accuracy of this one with the same bit precision configuration. It can be attributed to the fact that in general under parameterized models do not perform well, and over parameterized models are prone to overfitting. The purpose of this exploration is to identify these discrepancies that would allow us to generate the best RTL model with the best power, performance, and area numbers. We also explored the effect of modifying the modes pertinent to quantization and overflow. Quantization and overflow logic may add extra hardware and latency to the design. We obtain 2 parameters from the RTL netlists prior and after the modification of logic. These parameters are MAE and area numbers. Next, we calculate the percentage change in MAE and area for 2 versions of the RTLs and try to observe the relation between them. In this experiment, we compare default quantization and overflow modes with the ones that is giving us better accuracy. As we observe in the table, for majority of cases, the percentage change in MAE is much higher than the percentage change in area. From the results, we can infer that the area savings we'd be having is much less significant than the ME penalty we'd be getting. But with prudent selection, one can try to choose modes for overflow and quantization logic. We also try to see the relation between latency and area as we constrain the loop. We observe, we take a sample network and progressively add parallelism to the design. As evident from the figure here, parallelism reduces latency cycles, but area requirement increases with that. Targeting least latency, we then synthesize the designs in commercial 65 nanometer process. We utilize commercial synthesized tool to obtain the corresponding power, performance, and area numbers. As we see from the plot Here, as expected, as we go towards bigger networks, the area and power consumption increases. Um, in regards to performance, we obtain latency in the range of 3 to 5 cycles. We also achieve a throughput of 1, that is, after the initial latency cycles, the new output comes out in each cycle. For our work, we maintain a clock frequency of 100 MHz as demanded by our application of peak prediction. With that, I want to conclude my presentation. First, we try to establish an ASIC design flow, the target application being to predict the peak amplitude of the sensor signal. We ensure a seamless transition from QQRS to gate-level synthesized design with minimal accuracy loss. We only observe variation of ME in the range of 0.2 to 1.2% between QQRS and HLS for ML, and 0% variation between HLS for ML and RTL. Secondly, we try to explore different aspects of this design methodology that enable us to choose the best network model for our use case. I would also like to put forward some acknowledgement. This work is supported by BNL, LDRD funding, a collaborative effort with Instrumentation Division and Computational Science Initiative.